In mathematics, the trigonometric functions are functions of an angle. They relate the angles of a triangle to the lengths of its sides. Trigonometric functions are important in the study of triangles and modeling periodic phenomena, among many other applications. The most familiar trigonometric functions are the sine, cosine, and tangent. In the context of the standard unit circle, where a triangle is formed by a ray originating at the origin and making some angle with the x-axis, the sine of the angle gives the length of the y-component of the triangle, the cosine gives the length of the x-component, and the tangent function gives the slope. More precise definitions are detailed below. Trigonometric functions are commonly defined as ratios of two sides of a right triangle containing the angle, and can equivalently be defined as the lengths of various line segments from a unit circle. More modern definitions express them as infinite series or as solutions of certain differential equations, allowing their extension to arbitrary positive and negative values and even to complex numbers. Trigonometric functions have a wide range of uses, including computing unknown lengths and angles in triangles. In this use, trigonometric functions are used, for instance, in navigation, engineering, and physics. A common use in elementary physics is resolving a vector into Cartesian coordinates. The sine and cosine functions are also commonly used to model periodic function phenomena such as sound and light waves, the position and velocity of harmonic oscillators, sunlight intensity and day length, and average temperature variations through the year. In modern usage, there are 6 basic trigonometric functions, tabulated here with equations that relate them to one another. Especially with the last 4, these relations are often taken as the definitions of those functions, but one can define them equally well geometrically, or by other means, and then derive these relations. Right-angle triangle definitions. The notion that there should be some standard correspondence between the lengths of the sides of a triangle and the angles of the triangle comes as soon as one recognizes that similar triangles maintain the same ratios between their sides. That is, for any similar triangle the ratio of the hypotenuse and another of the sides remains the same. If the hypotenuse is twice as long, so are the sides. It is these ratios that the trigonometric functions express. To define the trigonometric functions for the angle A, start with any right triangle that contains the angle A. The 3 sides of the triangle are named as follows. The hypotenuse is the side opposite the right angle, in this case side H. The hypotenuse is always the longest side of a right-angled triangle. The opposite side is the side opposite to the angle we are interested in this case side A. The adjacent side is the side having both the angles of interest, in this case side B. In ordinary Euclidean geometry, according to the triangle postulate, the inside angles of every triangle total 180 degrees. Therefore, in a right-angled triangle, the 2 non-right angles total 90 degrees. So each of these angles must be in the range of as expressed in interval notation. The following definitions apply to angles in this 0 degrees to 90 degrees range. They can be extended to the full set of real arguments by using the unit circle, or by requiring certain symmetries and that they be periodic functions. For example, the figure shows sim for angles theta, pi minus theta, pi plus theta, and 2 pi minus theta depicted on the unit circle and as a graph. The value of the sine repeats itself apart from sine in all 4 quadrants, and if the range of theta is extended to additional rotations, this behavior repeats periodically with a period 2 pi. The trigonometric functions are summarized in the following table and described in more detail below. The angle theta is the angle between the hypotenuse and the adjacent line, the angle at A in the accompanying diagram. Sine, cosine and tangent. The sine of an angle is the ratio of the length of the opposite side to the length of the hypotenuse. In our case, this ratio does not depend on the size of the particular right triangle chosen, as long as it contains the angle A. Since all such triangles are similar, the cosine of an angle is the ratio of the length of the adjacent side to the length of the hypotenuse, so called because it is the sine of the complementary or co-angle. In our case, the tangent of an angle is the ratio of the length of the opposite side to the length of the adjacent side, so called because it can be represented as a line segment tangent to the circle, that is, the line that touches the circle. From Latin linear tangens or touching line. In our case, the acronyms SOHCAH TOA and OHSAHCOAT are commonly used mnemonics for these ratios. Reciprocal functions. The remaining three functions are best defined using the above three functions. The cosecant CSC, or cosec, is the reciprocal of sin, i.e., the ratio of the length of the hypotenuse to the length of the opposite side, so called because it is the secant of the complementary or co-angle. The secant sec is the reciprocal of cos, i.e., the ratio of the length of the hypotenuse to the length of the adjacent side. It is so called because it represents the line that cuts the circle. The cotangent cot is the reciprocal of tan, i.e., the ratio of the length of the adjacent side to the length of the opposite side, so called because it is the tangent of the complementary or co-angle. Slope definitions equivalent to the right triangle definitions. The trigonometric functions can also be defined in terms of the rise, run, and slope of a line segment relative to horizontal. The slope is commonly taught as rise over run, or rise, run. The three main trigonometric functions are commonly taught in the order sine, cosine, tangent, with a line segment length of 1. The following mnemonic devices show the correspondence of definitions. Sine is first, rise is first, meaning that sine takes the angle of the line segment and tells its vertical rise when the length of the line is 1. Cosine is second. Run is second, meaning that cosine takes the angle of the line segment and tells its horizontal run when the length of the line is 1. Tangent combines the rise and run, meaning that tangent takes the angle of the line segment and tells its slope, or alternatively, tells the vertical rise when the line segment's horizontal run is 1. This shows the main use of tangent and arctangent. Converting between the two ways of telling the slant of a line, i.e., angles and slopes. While the length of the line segment makes no difference for the slope, it does affect rise and run. To adjust and find the actual rise and run when the line does not have a length of 1, just multiply the sine and cosine by the line length. For instance, if the line segment has length 5, the run at an angle of 7 degrees is 5 cos units. Circle definitions. The six trigonometric functions can also be defined in terms of the unit circle, the circle of radius 1 centered at the origin. The unit circle relies on right triangles for most angles. The unit circle definition does, however, permit the definition of the trigonometric functions for all positive and negative arguments, not just for angles between 0 and pi, 2 radians. From the Pythagorean theorem, the equation for the unit circle is let a line through the origin, making an angle of theta with the positive half of the x-axis. The line intersects the unit circle at a point P whose x and y coordinates are cousins, and let us consider the right triangle whose vertexes are the point P, the center of the circle O, and the point H of the x-axis, that has the same x-coordinate as P. The radius of the circle is equal to the hypotenuse OP, and has length 1, so we have sin equals y, 1 and cos equals x, 1. The unit circle can be thought of as a way of looking at an infinite number of triangles by varying the lengths of their legs but keeping the lengths of their hypotenuses equal to 1, for any angle theta and any integer k. The smallest positive period of a periodic function is called the primitive period of the function. The primitive period of the sine or cosine is a full circle, i.e., 2 pi radians or 360 degrees. Above, only sine and cosine were defined directly by the unit circle, but other trigonometric functions can be defined by. So, the primitive period of the secant, or cosecant is also a full circle, i.e., 2 pi radians or 360 degrees. The primitive period of the tangent or cotangent is only a half circle, i.e., pi radians or 180 degrees. The image at right includes a graph of the tangent function. Its theta-intercepts correspond to those of sin, while its undefined values correspond to the theta-intercepts of cos. The function changes slowly around angles of k-pi, but changes rapidly at angles close to pi. The graph of the tangent function also has a vertical asymptote at theta equals pi, the theta-intercepts of the cosine function. Because the function approaches infinity as theta approaches pi from the left and minus infinity as it approaches pi from the right. Alternatively, all of the basic trigonometric functions can be defined in terms of a unit circle centered at O, and similar such geometric definitions were used historically. In particular, for a chordab of the circle, where theta is half of the subtended angle, sin is AC, a definition introduced in India. Cos is the horizontal distance OC, and versin equals 1 minus cos is CD. Tan is the length of the segment A of the tangent line through A, hence the word tangent for this function. Cot is another tangent segment, AF. Sec equals OE and CSC equals of the segments of secant lines, and can also be viewed as projections of OA along the tangent at A to the horizontal and vertical axes, respectively. Der is x sec equals sec minus 1. From these constructions, it is easy to see that the secant and tangent functions diverge as theta approaches pi, 2, and that the cosecant and cotangent diverge as theta approaches 0. Algebraic values. The algebraic expressions for sin, and sin are respectively. Such simple expressions generally do not exist for other angles. For an angle, which, measured in degrees, is a multiple of 3, the sine and the cosine may be expressed in terms of square roots, as shown below. These values of the sine and the cosine may thus be constructed by ruler and compass. For an angle of an integer number of degrees, the sine and the cosine may be expressed in terms of square roots and the cube root of a non-real complex number. Galois theory allows to prove that, if the angle is not a multiple of 3 degrees, non-real cube roots are unavoidable. For an angle, which, measured in degrees, is a rational number, the sine and the cosine are algebraic numbers, which may be expressed in terms of nth roots. This results from the fact that the Galois groups of the cyclotomic polynomials are cyclic. This is a corollary of Baker's theorem, proved in 1966. Explicit values algebraic expressions for 15 degrees, 18 degrees, 36 degrees, 54 degrees, 72 degrees and 75 degrees are as follows. From these, the algebraic expressions for all multiples of 3 degrees can be computed. For example, algebraic expressions can be deduced for other angles of an integer number of degrees, for example, where z equals a plus ib, and a and b. The above algebraic expressions for, respectively, cos 3 degrees and sin 3 degrees, and the principal cube root is to be taken. Series definitions. Trigonometric functions are analytic functions, using only geometry and properties of limits. It can be shown that the derivative of sine is cosine and the derivative of cosine is the negative of sine. One can then use the theory of Taylor series to show that the following identities hold for all real numbers x. The infinite series appearing in these identities are convergent in the whole complex plane and are often taken as the definitions of the sine and cosine functions of a complex variable. Another standard definition of the sine and the cosine as functions of a complex variable is through their differential equation, below. Other series can be found for the following trigonometric functions. Un is the nth up-down number, Bn is the nth Bernoulli number, and n is the nth Euler number. Tangent, where this series for the tangent function is expressed in a form in which the denominators are the corresponding factorials. The numerators, called the tangent numbers, have a combinatorial interpretation. They enumerate alternating permutations of finite sets of odd cardinality. The series itself can be found by a power series solution of the aforementioned differential equation. Cosecant secant, when this series for the secant function is expressed in a form in which the denominators are the corresponding factorials. The numerators, called the secant numbers, have a combinatorial interpretation. They enumerate alternating permutations of finite sets of even cardinality. Cotangent from a theorem in complex analysis, there is a unique analytic continuation of this real function to the domain of complex numbers. They have the same Taylor series, and so the trigonometric functions are defined on the complex numbers using the Taylor series above. There is a series representation as partial fraction expansion where just translated reciprocal functions are summed up, such that the poles of the cotangent function and the reciprocal functions match. This identity can be proven with the Herglotz trick. Combining the th with the nth term led to absolutely convergent series relationship to exponential function and complex numbers. It can be shown from the series definitions that the sine and cosine functions are, respectively, the imaginary and real parts of the exponential function of a purely imaginary argument. That is, if x is real, we have and the latter identity remains valid for a non-real x, and is called Euler's formula. Euler's formula can be used to derive most trigonometric identities from the properties of the exponential function, by writing sine and cosine as. It is also sometimes useful to express the complex sine and cosine functions in terms of the real and imaginary parts of their arguments. This exhibits a deep relationship between the complex sine and cosine functions and their real and hyperbolic real counterparts. Complex graphs. In the following graphs, the domain is the complex plane pictured, and the range values are indicated at each point by color. Brightness indicates the size of the range value, with black being 0. Hue varies with argument, or angle, measured from the positive real axis. Definitions via differential equations. Both the sine and cosine functions satisfy the differential equation. That is to say, each is the additive inverse of its own second derivative, within the two-dimensional function space V consisting of all solutions of this equation. The sine function is the unique solution satisfying the initial condition, and the cosine function is the unique solution satisfying the initial condition. Since the sine and cosine functions are linearly independent, together they form a basis V. This method of defining the sine and cosine functions is essentially equivalent to using Euler's formula. It turns out that this differential equation can be used not only to define the sine and cosine functions but also to prove the trigonometric identities for the sine and cosine functions. Further, the observation that sine and cosine satisfies y equals minus y means that they are eigenfunctions of the second derivative operator. The tangent function is the unique solution of the nonlinear differential equation satisfying the initial condition y equals 0. There is a very interesting visual proof that the tangent function satisfies this differential equation. The significance of radians. Radians specify an angle by measuring the length around the path of the unit circle and constitute a special argument to the sine and cosine functions. In particular, only sines and cosines that map radians to ratios satisfy the differential equations that classically describe them. If an argument to sine or cosine in radians is scaled by frequency, then the derivatives will scale by amplitude. Here, k is a constant that represents a mapping between units. If x is in degrees, then this means that the second derivative of a sine in degrees does not satisfy the differential equation but rather the cosine's second derivative behaves similarly. This means that these sines and cosines are different functions, and that the fourth derivative of sine will be sine again only if the argument is in radians.